So let's take a look at integration of rational functions by partial fractions, or in other words, integration by partial fraction decomposition. Now, what partial fraction decomposition allows you to do is it allows you to break up a fraction into two or more smaller fractions, so that's easier to integrate. And keep in mind that partial fraction decomposition only works on fractions that are bottom heavy, meaning the highest degree of the denominator is greater than the highest degree of the numerator. So now for number 1, we have the integral of x minus 9 over x plus 5 times x minus 2 dx. Realize that the highest degree of the denominator, when I FOIL this, we get x squared as the highest degree. That is going to be greater than the highest degree of the numerator, which is x to the first, so we can use partial fraction decomposition on this problem. Now the first step for doing partial fraction decomposition is we're going to rewrite what's inside the integral. So we don't even have to worry about the integral at the moment. First we got to break up this fraction. Now the next step is we're going to set it equal. Now it depends on how many factors you have on the denominator. In this case we have two linear factors, x plus 5 and x minus 2, so we're going to break it up into two separate fractions. So we set it equal to a, which is one constant, over one of the factors, x of plus 5, and then plus b, another constant, over another one of the factors, which is x minus 2. Now the next step is to get rid of the denominator on the left side of the equation. So I'm going to go ahead and multiply both sides of the equation by x plus 5 times x minus 2. Go ahead and multiply by x plus 5 times x minus 2 on the right side as well. So realize that will cancel, and so we're left with x minus 9 on the left side of the equation. And now on the right side of the equation, we can go ahead and distribute to each of the terms. So when I distribute to the a term, x plus 5 will cancel. So we're left with a times the other factor, x minus 2. And then plus, well, when we distribute to the b, the x minus 2 factors will cancel, and so we're left with b times x plus 5, the other factor. So now I need to make sure I keep the a and b terms here, or the a and the b fractions, because I'll use that for later. So now looking at this right here, what we need to do is pick something for x that will cancel out one of the terms and lead us to find out what the other term is. So in this case, if I plug in 2 for x, 2 minus 2 is 0, that will cancel out the a. So let's go ahead and do that. If I plug in 2 for x, we'll get 2 minus 9, so that's going to be negative 7, equals, well, 2 times 2 minus 2 is 0, 0 times a will cancel, and then we'll get 2 plus 5, which is 7, then we'll get negative 7 equals 7b. So then if I isolate b, we can say that b equals negative 7 divided by 7, or negative 1. Now the same thing I'll do for the a term. I'll pick something that will cancel out the b term so that I can find what the a term is. So in other words, I'll plug in negative 5 for x, because negative 5 plus 5 is 0, that will cancel. So then negative 5 minus 9 is negative 14, equals negative 5 minus 2 is negative 7, so negative 14 equals negative 7 times a. So if I go ahead and isolate a is going to be equal to 2. So now what I can do, given this information, is go back to the decomposed model, and then I can fill in for a and b. So once again, a is going to be equal to 2, so I have 2 over x plus 5. Then we have plus b is negative 1, so negative 1 over x minus 2. I can also bring that negative 1 out front. So we have 2 over x plus 5 minus 1 over x minus 2. So now I have broken this entire fraction up into two smaller fractions. And if I go ahead and put that underneath the integral, now it's much easier to integrate. So now the integral of 2 over x plus 5, 2 is just a constant, so it's going to be 2 times the natural log of the absolute value of x plus 5. And then we have minus the integral of 1 over x minus 2, that's just going to be natural log absolute value of x minus 2. Since this is an indefinite integral, I need to add the plus c, and that's the final answer. So now for number 2, let's say we have the integral from 2 to 3 of 1 over x squared minus 1 dx. Since this is a bottom heavy fraction, we can go ahead and use partial fraction decomposition. So the first step here is to rewrite what's inside the integral, so we don't need to worry about the integral right now. Now, in the previous problem we had distinct linear factors like x plus 5 and x minus 2. Realize that x squared minus 1 is a difference of squares, so I can go ahead and break that up into 1 over x plus 1 times x minus 1. So now we have two distinct linear factors, so now we can go ahead and use partial fraction decomposition. Once again, I'm going to set it equal to an a term over one of the factors, so x plus 1, plus another b term over the other factor, x minus 1. Now once again, in order to get rid of the denominator, I need to multiply both sides of the equation by x plus 1 times x minus 1. Go ahead and write that on the other side as well. Now those two will cancel, so we get 1 on the left side of the equation equals, now a shortcut here is just to cross multiply. So a will be combined with x minus 1, and then we have plus b that will be combined with x plus 1. So once again, I need to pick certain values for x so I can cancel out one term and evaluate the other term. So let's go ahead and start by plugging in 1 for x. So when I plug in 1 for x, we get 1 equals 1 minus 1 is 0, 0 times a will cancel, and then we'll get 1 plus 1, which is 2, so 1 equals 2 times b. So that tells us that b equals 1/2. So now let's go ahead and do the same to find out what a is. So I'm going to plug in negative 1 for x this time. That will cancel out the b term. Negative 1 plus 1 is 0. 0 times b is 0. So we get 1 equals negative 1 minus 1 is negative 2. So 1 equals negative 2 times a. So we get that a equals negative 1/2. So if I come back to the decomposed model and go ahead and sub in the terms, so a is negative 1/2. So we get negative 1/2 over x plus 1 plus b is going to be 1/2 over x minus 1. Since we have broken this up into this decomposed fraction, we can go ahead and integrate with respect to x. So now remember, the bounds of the integral were from 2 to 3. So let's go ahead and integrate now. Negative 1/2 is just a constant. So the integral of negative 1/2 over x plus 1 is going to be negative 1/2 times the natural log of the absolute value of x plus 1. And then we have plus the integral of 1/2 over x minus 1. Since 1/2 is just a constant, it's going to be 1/2 natural log absolute value of x minus 1. So now I'm going to go ahead and switch the order of the terms. So we have 1/2 natural log, I'll put first x minus 1, and then minus 1/2 natural log absolute value of x plus 1. So I'll rewrite it as 1/2 times natural log absolute value of x minus 1, and minus natural log absolute value of x plus 1. So now, using properties of logs, whenever you have a natural log minus another natural log, you can go ahead and just divide the terms that are inside of the natural logs. So I can rewrite it as 1/2 natural log absolute value of x minus 1 over absolute value of x plus 1. Since the numerator and denominator both have absolute values, I can erase those and then put the entire fraction under an absolute value, or inside an absolute value. So now let's go ahead and evaluate from the x bounds of 2 to 3. So we get 1/2 times, now when I plug in 3 for x, we'll get ln of 3 minus 1, which is 2, over 3 plus 1, which is 4. So I can rewrite it as ln of 1/2, and absolute value of 1/2 is just 1/2. And then minus, when I plug in 2 for x, we'll get 2 minus 1, which is 1, over 2 plus 1, which is 3. Absolute value of 1/3 is just 1/3. So now rewriting and simplifying for the answer. Once again, properties of logs we can use here because there's a minus or a log minus another log. So we can go ahead and divide 1/2 by 1/3. So we can go ahead and rewrite it as 1/2 times the natural log of 1/2 divided by 1/3, which is going to be 3/2. And that's the final answer.